Hello and welcome back. In this example, we're looking at related rates once again. And this time around, we have a problem where we have two people who are walking away from each other, starting at the same point, and they're both walking at a constant rate, which is extremely important in this problem. And we're going to find out at what rate the distance between them is changing. So to do this, we're going to first start off with a diagram because, again, diagrams make these problems much more simpler to do. So we're going to have the displacement or distance north that our person's walking and our distance east that they're walking. So we're going to let x of t represent the horizontal or eastward distance. And we're going to let y of t represent the distance of the person walking northbound. And then we will let z of t represent the diagonal distance between those two people. So we're going to let z of t be this diagonal true distance between the two people. And because one is walking due east of the other person walking due north, we know that we have ourselves a right triangle. So our distances actually satisfy the Pythagorean theorem because we have a right triangle. And that theorem says that the sum of the squares of the legs equals the square of the hypotenuse. So in that case, writing it with function notation, we're going to have our x of t squared plus our y of t squared is equal to z of t squared. And again, this is a relationship that is satisfied or held for all values of t. So in particular, at this one moment in time, which is the 2-hour mark, we have to have our distances substituted in to find the distance between the two people. So after the 2-hour mark, which is t equals 2, our horizontal, or our distance going east, is going to be 8 miles. And then our distance north is going to be 6 miles. And again, our distance between them, we don't know. So we're just going to call that z of 2. And again, that is squared. So we can now square and sum these up. We know that 8 squared is 64. So that's 64 miles squared. And then we're going to have our 36 miles squared. And that is equal to z of 2 squared. And if we sum up 64 and 36, we get 100. So this is 100 miles squared is z of 2 squared. So we know that z of 2 is equal to the square root of 100 miles squared, which is just 10 miles. So at that one moment in time, they are precisely 10 miles apart. That is a lot of walking. All right, so the next thing to do is now turn this back into our calculus problem, and we have to talk about the rates. So we can take our equation, which we know, and again, we'll just write it back over here. That's x of t squared plus y of t squared equals z of t squared. And so now we can take the derivative of both sides of this equation with respect to time. And again, it's sometimes helpful to write this as a d dt, just to remind ourselves that we're differentiating with respect to time. So in doing so, using the chain rule, we're going to have 2 times x of t times the derivative of the inside, which is x prime of t, plus 2 times y of t times the derivative of the inside, y prime of t, equals 2 times z of t times the derivative of the inside, z prime of t. And now what we can do is do a little bit of simplification. We can divide this whole equation through by 2. And we can also go through and think about what we're trying to solve for. And in this case here, we are solving for the rate of change of the distance between them. So we are trying to find z prime of t. So we need to algebraically isolate it. And we're almost there. All we have to do is go through and divide both sides of the equation by z of t. So z prime of t is equal to x of t times x prime of t plus y of t times y prime of t divided by our z of t. And we can now substitute all of these rates in. And again, we're looking at the 2-hour mark here. So we're going to say this is z prime of 2. So after 2 hours of walking, we go back to the problem, and it says that we end up going east 8 miles. So that's going to be our 8 miles. And then our rate of change for walking east is going to be the amount of distance we walked divided by the amount of time we spent walking. And again, we're assuming everything is constant here. So this is going to be our 8 miles over a 2-hour period. We'll do the same thing for the distance walking north. So we know that we walked 6 miles north, and we walked those 6 miles north over a period of 2 hours. And then we just calculated a few minutes ago the fact that the z of t, or z of 2, is 10 miles. So now we can calculate z prime of 2, and that's going to be 8 times 4, which is 32 square miles per hour. And then we're going to have our 6 times 3, which is 18 square miles per hour, divided by a total of 10 miles. Simplifying this out, we get 32 plus 8, which adds up to 50. So we've got 50 square miles per hour divided by 10 miles, and that's going to be equal to 5 miles per hour. And that is the rate of change of the distance between the two people. That's the rate of change that the distance is changing between the two people. Make sure you say that correctly. All right, so let's go back to the problem and see if that makes sense. First of all, the units make sense because that is a rate of someone walking would be miles per hour. And if we go back to the problem, we notice that we use all the information in the problem that was given to us to find the rate of change of the distance between them. So that is our problem in its entirety.